All right. The thing is red. That means that we're on. All righty then. Hi guys, what's going on? Memes here. So, yes. We're going to expound upon some of the stuff and things that we were talking about last week. Let's say we're going to extend our really large number hypothesis and or I'm going to continue to speak to try to refine these thoughts in my mind as well as when I've just run up to a moment or I'm completely wrong. Chat holds me accountable. Why? Because I'm a crazy person on the internet. I'm a human being. I'm perfectly imperfect, like the rest of us. Maybe not all, but here's what we're going to do today. We're going to let folks join on in from all across the interwebs, from the YouTubes, from the X Twitters, from the blue skies, from wherever somebody may come across this link or the algorithm happens to recommend this for some apparent reason. But today, what we're going to be talking about, no, not negative time. That was yesterday. So I'm going to, where's that eraser? Yes, it's behind all the obscure things that I'm totally hiding on my desk. Why is there a bottle of ketchup there? Well, obviously because I am single. Personal shortcomings aside, we're going to talk about universe, small u universe, because we're going to put a number on something. Why? Because some numbers happen to line up in a very interesting way, and I feel this is something that should be more out there in the public consciousness. And to be fair, if you happen to have your own particular model and this happens to help, by all means, it would be nice if you gave maybe a shout out where it came from. And I'm just saying, some other folks have totally seen things like this before, and I'm just putting it out there into the ether. But and by ether, I mean space time or medium, because we all know it's totally not the ether. What may be more poetic justice is who knows, maybe it'll end up being a four-dimensional platonic solid. I know was it Nick Merzen, I think, from the Wolfram Institute. He's like, what is the smallest object I can use to help model qubits? Well, apparently the 600 cell. What's that? The hypericosahedron. Wait a second. You're saying a four dimensional D20 may literally be able to help model reality? Well, he has a paper and everything. I need okay, at the beginning of the year, I need to invite Nick on at some point. Just because it's such a fantastical thing. And again, I am very biased on this. Why? Because probably still the craziest calculation I ever did that gave me something was okay, well, if there is something to what Thad is saying within his model about using the base of natural logarithms to model the Planck constants, if we're going to say this is a theory of derangements, basically a set number of things that you can arrange in a particular different ways, what's something that's in common with all the different equations? Well, it has to be basically that little inversion box. Okay, we'll do a quick tangent on this. What am I talking about? The inversion box. What does this inversion box means? Okay, that's this little box we have here. And again, I know in mathematics and stuff that means different things. That's the thing that we're using for now. What is this box? This box is equal to the Planck mass, m sub p, times the Planck length, L sub p, all over the Planck charge, Q sub p squared. Okay, so rather than looking at the actual dimensional things, we're looking at the power. So the Planck mass is an absolute magnitude of 8. Because we take the absolute magnitude, that's 10 to the negative 8, this is 10 to the negative 35, this is 10 to the negative 18. We take the absolute magnitude of the Planck length, which is 35. Okay. And then the Planck charge squared, well, that's that's 18 and 18. So that's, what was that? Oh God, I have to do more math in my head. I think is it like 288. It's something like that. Oh, okay, well it's 18 there, and then 18 there again. Magnitudes. Okay. Long story short is when you do that thingy, that comes out to be a rational solution of 70 over 81. Again, I get this result. I have no idea what it means. Okay. So I literally toss it into Wolfram Alpha, and then you end up getting 35 over 6. How is it? T sub 20 VE. The 20 no, it's 20. T20 VE. No, actually no, it's the bottom one, I think. T20 VE. What is that? The 20 vertex entropy constant. For some reason, that's like that something with 20 vertices. What might that be? Oh yeah, it was squared. Okay. Uh Long story short, I'm like, well, 35. We're saying that's the derangements of this thingy here, derangements of length. All right, so that's a length characteristic thing. All right, what's it divided by? 620 vertex entropies. I'm like, well, six, and then 20 vertices. I'm like, that makes 120. Oh, this is the most ridiculous numerology I think I've ever seen. The terrifying thing is there might be something there. I can't say. That's why I get the result. I'm like, wait, what do I even do about this? I can't do this as like a full video. Maybe I did. All right, hold on. Let's because this is the fantastical thing. All right, so let's. Oh, I should probably actually open up another tab if I'm gonna claim to do a fantastical thing. All right, let's do it. Boom. All right, so I go to Wolfram Alpha. What am I talking about? All right, so we're taking what is it? The Planck mass. So Planck mass. Just to confirm, what is this thingy within the system of kilograms? -8. It's got a magnitude of 8. Okay. Let me take the length, length. What's the magnitude of the exponential power? 35. All right. We got 8 and 35. Now we just need the Planck charge. What's its magnitude? Yeah, you can feel free to trust, but verify. I feel like that's the thing people used to say. All right. It's got a magnitude of 18. So we're doing this, and well, what is that? That's if you do this, let me just do like mass, like length over like charge squared. We have our brackets there because I like brackets. Okay, you get approximately 10 to the -7. Full disclosure, this answer is very close. They're like the first 6 significant digits, and then on the 7th digit has a very slight deviation. It goes from like matching it by like 0.99999929999. Uh, it's a pretty crazy thing, but where are we here? Oh, hey, welcome, KK. KK is addressing us. Oh, hey, good to show you. Hey, Charlie, we had to update things. It's good to see you, my friend. We're not talking about negative time at the moment. Uh oh, oh, the 600. Wait a second. This okay, that is very weird. Apparently, Mr. Grant, I missed Mr. Grant Gregory's comment from earlier, and oh God, wait, is he from the future or the past? I forget from whence he hails. I'm just seeing 600 cell, and I did not even notice that until now. I actually, Poindexter, thank you for joining, and I had been answering Kali in the chat there. She had been commenting. When I go big and say infinite, it's like, all right, when we say infinite, I'm willing to conjecture infinite in time. What does that mean? That means essentially the only potential perpetual motion machine we could have would be reality itself. And again, that might be wrong. I'm sure it would. Okay, where are we getting? Oh, the little box thing. It's essentially it's the Ampere constant. Okay, aka magnetic permeability. We might end up figuring out how magnets even work, my friends. I think that would be a really neat thing. All right. But yes, hey, welcome, Rick. Yes, we're what am I expositing on? Where I'm slowly getting to the point. Okay, I'm in a tangent story right now about apparently the first thing that Mr. Grant Gregory had mentioned that I didn't even see in the chat, something about the 600th cell. Um, and we're attempting to connect four-dimensional platonic solids to reality. Apparently, Nick Merzen from the Wolfram Institute found that the smallest group structure he could use to model qubit-based systems was the 600 cell, which is essentially a four-dimensional icosahedron. I'm trying to make the numerological link, and again, numerology is numerology until it explains more with less. Okay. But this whole little box with a Planck mass times a Planck length times a Planck charge squared, basically, what was it, last summer, where I'm sitting there, I need to figure out something. I need to figure out something. It's what's something that we know? Oh, we've looked at this. I've put together, spent far too much time looking at it. And I'm like, eventually, I literally just take the equations, throw it in a Wolfram notebook. But the equations were set equal to the magnitude of their powers. Like the Planck mass, the equation was set equal to 8. The Planck length was set equal to the magnitude of its power, 35. And the Planck charge was basically just its magnitude squared. All right, so it was 18 squared. Long story short is, hold on, long story short is, since I threw in a bunch of integers and divided it by an integer, I got a rational solution. What is it, 70 over 81? Doesn't mean a dang thing to me. You put it into Wolfram Alpha, and here's where we're getting to. We're going to get to. So that's the calculation there. So all we're going to do is replace this Planck mass. It was an 8 for its magnitude of its exponent. The Planck length is 35 for its exponent. That should automatically do. Oh, hold on. I should actually share rather than just blather words for no incoherent reason. All right, and then we're going to take the Planck charge. I'm going to put an 18 there. Okay, and we're squaring it. Then we get our answer. What's that? That's the answer over the board again. I have no idea what that means. Maybe if I click on it, it'll do something funny or something useful. Wolfram Alpha, what is this number? What could its potential closed forms be? 70 over 81. Okay, we saw that. The 700 Wadsworth constant, well, that's like 0.333 repeating or something like that. Okay. Is there something that might, what the? Pardon. All right. What is this? 35 divided by 620 vertex entropy constant squared. And this approximation appears to be the same number. This was the calculation where I literally went WTF, mate. Reason number one. This constant here, hold on. Yes, trust us verify. The 20 vertex entropy constant. What the heck is that thing? All right. 20 vertex entropy constant. All right. So basically, you're setting L. You got an L there. What is that? That's the thing we're representing. Denote an n by n triangular lattice with wraparound. So it's a lattice. Sounds like it's wrapping around on itself. I don't know. Is there Mobius twist or something? Okay. Long story short is it's this thingy. And they named it here. And okay, wait. Why is that significant at all? It has, okay. Under the comments from the online encyclopedia of integer sequences. All right. Equivalently, the area on the complex plane of the smallest convex set containing all order 6 roots of unity. Sounds a little like the imaginary golden ratio there. Okay. Some stuff here. And then all of a sudden, out of the blue, like 2 years ago or so, Lana proves that this is the critical impact parameter of a bare black hole. In multiples of the Schwarzschild radius, that is, light from a distant source coming toward a black hole is captured by the black hole at smaller distances and deflected at larger distances. There's some other math stuff involved here. Oh my God, they're finding additional stuff on it. I love the internet. Okay. Again, what the heck does that mean? All right. It's got cool stuff associated for properties that people apparently have found useful. Okay. Hey, K-Shaw. What's going on? Oh, listen, nerdy. You may have been around long enough to know that lettuce is still slightly triggering to me. It's okay. It was a traumatic experience at Disney World, but that's not for today's show. Okay. Oh. Oh, hey, David. Howdy, everybody. Yes. Just commenting, Mason. 5 times 5 factorial. 5 times 126. Metal. Yellow. First. Red. I'm still parsing that. That's fascinating. All right. The old noggin is a dry. Okay. What the heck is the point of this? All right. Well, this is the whole claim is this magical box right here. This Planck mass divided by the Planck length over the Planck charge squared, which is supposed to give us Ampere's constant. Number one, there's very slight deviation between it being 10 to the negative 7 and it being almost. It happens at the seventh significant digit. Might that be significant? I'm biased. I think there might be a little bit. Okay. But the whole thing is that if what he's doing, if there is something to that, if these logarithmic bases that we've covered before in previous videos, or the whole like board full of math, if these things we're saying they're exponential powers are things that we could count or arrange in particular ways, if there is something to this, maybe we might find something within the equation that's basically in the whole poster of like 288 or so constants. Okay. This happens when you do that math and you just do 8 times 35 divided by 18 squared, you get this thing here, 70 over 81, which also has the closed form of 35. So 35, what's that? Oh, that's a number of derangements for space. All right, so that's a space stuff. The space stuff, something to do with space, is divided by 6 times the 20 vertex entropy constant. All right, 6 times 20 vertices is 120. What? Are there objects with 120 vertices? 120 vertices. Okay. So, okay, well, that's edges, blah, 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 blah. Hold on, we'll go through. They don't make this easy. At first, I found the 120 cell, which don't worry, we'll get back to it. But the 120 cell, because that sounded cool. To be fair, it only has it has 600 vertices. That's not 120. To get 120, we need its dual, the 600 cell, which is the four-dimensional platonic solid that Nick used in his Wolfram model for qubits. It seems to be the smallest one necessary. Now, the interesting thing is we have that stuff, but remember, it's the 20 vertex entropy constant squared. I don't know. Might that suggest a double cover or perhaps a mirroring of sorts? What might be going on? Might it be the 600 cell, which I believe is the second largest four-dimensional platonic solid, whose dual is the 120 cell that has 600 vertices, which is the largest four-dimensional platonic solid. So that was a fun jaunt at numerology and stuff like that. And it's just, if that does pan out, I mean, I think that's a very interesting thing. Again, it's such a fantastical thing that I really can't talk about it seriously, except for taking about the first 15 minutes of this discussion to do so. A little side jaunt. 86 400. See, that's a very interesting thing. It's not quite, some folks say we should do a 13-month calendar. Listen, politics of time aside, oh God, the politics of time. This is the shades of E8. Well, it kind of reminds me of that. All right. But that's not what we're here for right now. We're here to talk about other crazy things. All right. So for other crazy things, we can take out our other crazy things, because our other crazy things is last week we were discussing really large number hypothesis. What was that? Well, Good old Professor Dirac had conjectured when you look at some of the parameters of the observable universe, like the amount of mass, and about as far as we can see, and you look at some of these relationships, you're getting some magnitudes that are around like 10 to the 40. Those are some really large numbers, and he had his own particular way of looking about things. And it's like, all right, well, what if there was something that we could conjecture in a way that would probably make sense, or at least be able to make sense enough to show maybe simple relationships? Because that's the thing. Because remember, numerology is numerology until you explain more with less. Now, I'm not saying it's not going to raise more questions. It raises a lot of questions for me, but occasionally, I believe it was Vanessa that said, nature is simple. If nature is simple, and I'm a simpleton, and I should be able to figure this out. Why? Because it's not just me. We literally have now access to like vast tools, but millennia of knowledge that people have worked so hard to get. And we got each other. I think that's a lot. I feel like I should start singing Bon Jovi here right now. And that's a lot for love. We'll give it a shot. Okay, that's why not why here. All right. So what happens if we just start doing some crazy conjecturing because we can? Let's start with something. What's something that we know? Well, let's try to figure out a size. How do we do that? We do that with a length. All right. What unit of length do we use? Well, in SI we use right bigger meters. I can increase my font. Oh my God, I can almost read that aside from the glare. All right. Meters. All right. Now, what if let's do something useful? Let's square it. So let's try to do a square meter. Why? Because this is our unit of length. Let's divide it by its minimum unit of length. What's the minimum unit of length in meters? That's the Planck length. I'm gonna write it out. Planck length. Okay. Because now this is dimensionlessly meters squared. If you divide it by a term that's in meters, you're going to get a meters term out or a unit of length. And that length happens to be, it's like, what is it? It ends up being about, what is it, 6.1, it's like 6 times 10 to the 34 meters. Okay. What the heck is that? That, my friends, is the conjectured radius of small u universe. That's why we get the 100 million times larger. Why? Well, let's literally just look at the number. Bring this back. We don't need you. And we literally just do what we did there. Meters squared divided by length. Okay, what does that give us? 6.187 times 10 to the 34 meters. That's a pretty big number there. All right, how does it compare? Oh, wait a second. That's only about 10 million times. All right, that's for a radius. The diameter of the observable universe, well, that would be 2 times radius. Let's multiply it by 2. What do we get? Oh, 1.237 times 10 to the 35. That would be the estimated diameter of small u universe. Okay. Okay. So we get 10 to the 8 there. What's that? Well, that would be 8 zeros. What's 8 zeros? Well, 3 zeros, you get 1,000. 6 zeros, you get 1,000,000. We need 2 more zeros. It makes it 100 million times larger than the diameter of observable universe. If it's 100 million times larger, it might be hard to check for curvature. I'm just saying, and again, why am I doing this? This is such a, oh, we're saying this is like a simple little thing here. what is the whole point? Well, the whole point is, let's do become even crazier. What can we do that's crazy? Oh, you're already doing the ridiculous thing of conjecturing that our realm of persistence, small u universe, is about 100 million times larger than our observable universe. Because let me just do this. Observable, observable universe. What's that? Spherical region, blah blah blah. How about this? Radius, observable universe. No! Radius. Hold on. I think I need to just. Do I need to change the. Okay. R sub U. All right. Radius of the observable. All right. So basically 10 to the 26 meters. What were we at? We were like 10 to the 34 ish. Yeah. So it's about 8 orders of magnitude if we do that. All right. So just about nine when we. And again, we're comparing in the different ways. So, all right. So we're basically 8 orders of magnitude larger. Okay. So that's 100 million times. Well, what if we extended our craziness and we took some inspiration from Rick DeWitt and Dr. Salvatore Pius? What do we do there? Well, let's say we've got this for a radius. What is that equation? Hold on. I got it. Oh God, I always forget. Hold on, we'll just do this. The Planck force one. Wait, no, it's in the description of this video. Hold on. Well, it'll be right back. Don't mind me. Straight. Pause that. All right. How big is the universe? All right. Uh, boom. Fastest way to get. Okay. So the claim is the Planck force is equal to massive universe times c squared. So you get mass energy of universe, and you're dividing it by this is our claimed radius, that meter squared of the Planck length that we have here. Okay. So we're just tossing in there. Okay. So we've got a thing we've conjectured. We've got c squared in Wolfram alpha. We've got the Planck force in Wolfram alpha. Hypothetically, how much mass should there be? All right. We solve for x. It gives us redonkulously ginormous numbers. Let's click. Oh, God. That's a lot of prime factorization. Okay, so what the heck is this ginormous number? It's kilograms. Okay. Help Wolfram alpha. Make this easier to understand. I can't count that many digits. All right, that many kilograms. It's that many grams. So grams is 3 orders of magnitude. All right, so that equals, okay. So about 8 times 10 to the 61 kilograms. All right, that's a bold claim. Is this number useful at all? Oh, my friends, let's go back to that. What if we conjectured something kind of goofy? Let's take our meters equivalent and let's do this. Let's just take that number. So that gave us a dimension of meters. Let's give us a dimensionless number because we're dividing the base unit of meters by its minimal meter. All right. So what if we did something nuts? We set it equal to, let's say, x kilograms. Let's use a mass term, the Planck mass. Divide it by that. Okay, because we know what meters is. We got the Planck length. We got the Planck mass. Let's solve for x again. Oh, I forget. Oh, I did something totally wrong. Oh, wait, no, I was supposed to. Pardon my squareness. Because we want to do a squared thing, so we look at the dimensionless relationship between these two. Okay. When you get a number really magnitude smaller, I made an error. Okay. Wait a second. This number looks pretty familiar. And again, with a slight rounding in there and everything, but go to it. That our kilogram tag. Let's see what we got. Wait a second. This number looks familiar. 0.33 times 10 to the 61 kilograms, but that was the number we got over here for that Planck force thingy. WTF, mate? What is going on here? Yes, yes, the research. Well, we had Michael Perone on, and he's happily in the flat universe, nerdy. So it's oh yeah, yes. WWKK is bringing up the I think the difference between the 600 cell and the 120 cell, in order for them to be at the same volume and I think edge length, the factor, listen, no, the edge length, in order for their volumes to be equal, I think it was like 8 golden ratios, or 8 divided into the golden ratio squared, something like that. Maybe 8 divided by the golden ratio squared or its conjugate. Um, that literally, yeah, the golden ratio was a factor bridging the 4-dimensional platonic solids, the hypericosahedron and hyperdodecahedron. I mean, it's just such a fantastical thing. I'm like, I have no idea if they. I mean, that would be poetic justice for Plato and a lot of the things that the ancient Greeks were saying, where it's like maybe there's something to this. Hey, maybe you just needed an extra dimension there. That was all. Hey, can't. All right, these things happen. But is it bigger than the inside nerdy? Nerdy. To be fair, if you do the calculation, so hypothetically, let's go here. Hypothetically, if you were to do a 4-dimensional hypersphere with these dimensions, you would get. Let's go. All right, so dimension 4 hypersphere in rest in 4 dimensions. Okay. Number 1, the area, quote unquote, the area on the outside, the area of its boundary or whatever it is equal to this. The content is equal to that. Literally, it's like a 2 pi squared relationship, because when open that guy, open that guy. Hold on. As soon as it gets to the 4th, it does wacky things here. Yes, because it. Yeah, you wind up too much there. Well, I'm just doing this. Let me divide that into that. Wait a second. What do we? What do we get here? Wait a second. This number looks kind of familiar. Looks kind of like our. Looks kind of like our radius here. Like our radius here. Copy it. All right, we got this number. Divide that number into our radius. What do we get? 0.25. Yeah, it's basically the dimension 4. Its difference is 4. Uh, I think that's it. It literally ends up being the same thing in like the same number of dimensions, because what is it? I think if we just take this ginormous number here, what is it? We take meters. Okay, let's get out some of that. There we go. Okay, now it's much easier to handle. Let's do our little thingy. Let's cube it. 2.43, blah, blah, blah. Where are we at? Okay, so it ends up, I think it's, take that, and surface area. Okay, I think this is, a second. Oh, this guy. Okay, here we go. 19.74. Oh, look, 2 pi squared. Okay. 7.4. It's 3.9. Okay, it looks pretty good. So it's basically a 2 pi squared relationship between that going up in the different dimensions. So technically they are equal. That's ultimately the weird thing about it. Or maybe it goes up by just literally the dimension n. Something like that. All right. So that, and again, that's grasping. I'm just looking. I just want to look at just numbers that we can just look at and be like, all right, here's an interesting calculation. Why isn't it an interesting calculation? Because if we just, oh God, how far do I have to go? Okay. Listen, I can do a graph here. We can do a graph. Ultimately, what is this? This is the magnitude of the Planck length squared, or the inverse of the Planck length squared. If we're going to claim some form of an inversion or something, maybe we need to do that. Okay. And what's that? Oh, the Planck masses inversion. Okay. We got to solve for x. Gives us this ginormous number, which appears to be this guy. Oh, no. We went too far ahead. There we go. This guy here. 0.33 times. Wait a second. If there was to be something through that, okay. Now how is okay? So that was squared, and that was normal. All right, but they always forget that. So, all right. So we do that. Let's change one thing. This one little trick we're gonna do is we're gonna erase. We're gonna do something crazy. We're gonna take our squared term. We're going to move it outside the parentheses. All right. There we go. That leads to basically 10 to the 69th power. Actually, 3 times 10 to the 69th power. All right. That's a very ginormous number, folks. Okay. Now, the claim is that we set that equal to, let's say, I got the Planck length on the bottom, so let's take the Planck mass. We'll put the Planck mass down below. We'll do the Planck mass. All right. How about this? Well, we need to solve for something. Do x kilograms. All right. And apparently, according to the maths, we do this. Okay. So this is meters up here. So we got meters divided by the Planck length. If we square that, it appears to be equal to the x kilograms, which comes out to be that 8 times 10 to the 61 number there that we also got from Rick and Dr. Salvatore Pais' Planck force little calculation there. Okay. So if we follow this through, that's at least the claimed mass that would be distributed throughout small u universe. That we would detect, that would basically give us our standard matter density within the concordance model and everything. So we really want to be bold. What we do is we take that, we erase our x kilograms here, and we conjecture that hold on, we should play it. Why? Well, because we're here right now, and well, buckle up, folks. We're gonna conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
we would get conjectured mass of the universe. That's, I mean, that's a fantastical thing to say. How the heck do you confirm this? Well, you would need to. Okay, we're claiming it's 100 million times larger. Could we measure curvature? I don't know. How far do we need to measure? How many more magnitudes do we need to measure? Is it 10 to the 10 to the 8? Is it 100? Do we need to go another 8 orders of magnitude in our detection levels or distances? Or I don't even know what. I'm not a cosmologist. That's Professor Keating. Um, And again, why do I do this? What is okay? You can say words. You can say conjecture math of the universe. What does that even mean? Okay, we're gonna need yes. You have some fancy coinkydinks and everything. It's like, all right, things seem to kind of line up and everything. We did it from one calculation method. We got it in another calculation method. I mean, that would perhaps increase our credence, as Professor Carroll might say. But what else do we have here? Let's see. Hex is commenting. The It from Bit approach. Here's the thing. I don't know. We talked a wee bit about that. I can't distinguish it at this point. I mean, does it really matter for us? I mean, it's. I played a lot of games. I'm very sympathetic to it. I'll leave it at that. All right. Oh. Oh my God. I thought you were first parroting Hex. Take me down to the Paradise City. It's like, I can understand how it worked in the Permutation City. I want to load and send it. Okay, it's at first I thought it was rhyming, and then here's the thing. I mean, if you put yourself out here enough, once the large language models start watching videos, I'm just saying it's any sufficiently advanced technology is indistinguishable from magic. Oh God, imagine the terror if a whole bunch of digital shadow clones of me started going around. Oh, that would be horrible. But how far do you okay. So nerdy, we're going to I did this earlier, so we're gonna totally touch upon that. There was a math meme going around that's like simply enter the last 4 digits of pi for the PIN number. It's a math joke. Why? Because pi goes on forever. Hypothetically speaking. What if there was a limit to pi? We believe it goes on forever, but could it go on beyond observable universe, or would we need to continue to get larger in order for pi to have more pi meaning? Well, I may or may not have actually. Where's the window? And this guy. No, we'll just do it again. All right. Go to hypothetically. Go to our friend. Go to our bookmark. Manager. Sphere. Okay. So let's say if we got like 30, and there's only like 32 digits in here. In theory, you're gonna need the correct number of digits. But for first level approximation, if this was radius of of universe, so to speak. All right, let's say let's do like the first 4 digits, because otherwise my brain's probably gonna explode from all those numbers. Okay. So yeah, and we're only looking for an approximation. All right. If we take that as radius of universe, well, we're gonna need to. How do we do a circle? We need 2 pi. Multiply it by 2 pi. All right, it gives us this many meters. Cool. Let's divide it by our minimum of length. Divide by the Planck length. So you're gonna need somewhere in the realm of 2 times 10 to the 70th digit of pi. So of course I see this. So I'm like, all right, let's digit of pi. Let's ask Wolfram Alpha. Okay. I think I need to actually take the. It's interpreting a little different. Let's just do grab you. Let's go here. All right. 10 to the 70th digit of pi. Result cannot be determined using current methods. Well, we don't have it written down to, to the 70th pi. Wait a second. I know they have it to a lot of digits. I feel like it might be not that far away. Hold on. Do we have the 60th digit? No. The 40th digit? 20th digit? What? Get the 100 something digit, or I'm just doing something wrong. Okay. Oh, I'm using it as an. Go back. I was asking it to give a digit in decimal form. My mistake. Okay. Okay, so it doesn't have that. It's gotta have at least the 10 billionth. Ah, okay, never mind. So that would be technically, hypothetically, a potential answer. So you only need like 10 to the 70th something magnitude of pi. According to that method, I'm sure it's much more involved in that. Oh, hey Dan. KK is also saying golden ratio divided by the Planck length. Oh yeah, because it's got the first couple of digits at 1.6. What is it? Golden ratio divided by the Planck length. Yeah, it's got like the first. Oh, well, that's an interesting thing. Because the golden ratio is 1.618. 0.618 and Planck length is 1.616. I think it's 1.616. 0.616. So, but it's again, we got orders of magnitude, but orders of magnitude. Okay. Okay, I did the Planck. Okay, that scared me for a second. I'm like, wait, we're just giving me a different answer. Golden ratio. Why is it? Okay, that was fun. Yeah, I mean these are interesting things. I don't know. Maybe you got to multiply it by a Giesecke constant or something. Uh, the amount of time that I've literally just gone on Wolfram Holes and be like, oh, am I falling? And very often, I assume it's just craziness. Let's get away from the craziness for just a second, shall we? Okay, it doesn't come up close enough to continue to garner my interest for the moment. Okay. But we're going to look at this. Why? Because this gives you a ginormous number. Let's take this ginormous number. All right. Might this mean something? If you were to have the mass of colloquial universe, might there be a calculation that might make more sense using this number? Okay. I played around a lot. I've had a lot of epic fails. Here's what seemed to fail the least. Divided by the Planck density. The ginormous number. Like 10 to like the 96th power of kilograms divided by meters cubed. Okay. Providing this some like mass to okay, wait a second. What's this number? Wait, 1.616. Hold on a second. Didn't WWKK just say something about this? Wasn't this the magnitude of the Planck length? Wait a second. Let's take this. Let's divide it by meters squared. Oh my god, it is the Planck length. The Planck length times 1 meter squared. Our base unit of measure in length squared seems to be the conjectured mass of universe, so then it's massy state or matter state as we know it. And again, it's speculation. Divided by the Planck density gives us the unit 1. You get 1 Planck length times meter squared. Because if we duplicate this and we just do Planck length times meter squared, 1.16 times 10 to the minus 35 cubic meters. Oh, you go back to divide by Planck. 1.16 times, 1.616 times 10 to the minus 35 cubic meters. Huh. This, again, I'm sure it's just a coincidence. I just remember first time I saw the Planck density, it's like, all right, what the heck is this thing supposed to be? So let's do Planck density. What the heck is this magic I'm to speak about? Density. It's not the density we're looking for. All right. Well, the standard definition: speed of light to the fifth, d5 divided by big G squared times the elementary unit of action, h bar. You get this 5 times 10 to the 96 kilograms divided by cubic meters. Ginormous number. And we happen to get 1 Planck length squared if we happen to use that conjectured value. And again, it's 100 million times larger. I just thought it was pretty neat. That's it's mostly oh god. Sorry, I'm so terrible with the chat. Hold on. People actually having fantastic conversations. Hold on. Okay, let's go through. Okay. Oh, tangents. Okay, maybe at the 12th digit. Coincidentally, there's something on Math World where if you're calculating the volume of the figure eight knot, there's some series, alternating series or something, where it says it's correct, but if you actually check, it deviates after the 12th significant digit. No idea why. Again, Thad's mostly conjecture. All right, we only really need 14 significant digits. We got 14 significant digits. We can probably map things out. But it does deviate on like maybe the 10th or 12th day. I forget exactly what it was, but it was very interesting. Some of the other series worked, but why would it be so close? But it sounds like there's some tangent thing going on. I don't know. This is from like a year or so ago. Well, things are processing as a wave pattern, yeah, depending on your dimensionality. That's one of the beautiful things about 3 dimensions of space. Things can get knotted and stuff. In 4 dimensions, it might be a wee bit harder. People are greeting each other. Excellent, excellent. Then is commenting, it's limited by the processor being used for the calculation. Now, this is highly speculative. Like there's some calculations you get where what's the processing power of said G? I may or may not have arbitrarily done some calculations with the Planck power and how within some calculations that kind of seems to come out for some magnitude. And again, I've had lots of speculations. You have an order of like operations of the craziness of stuff that we look at and we deal with. Okay. Let's say if you're trying to find something, maybe it's not even new. Maybe just somebody discovered it years ago and they're just like, oh, isn't that an obvious thing? I think people criticize either Dick Feynman or there's some mathematicians in history where it's like you go through some of the notebooks and you look at this calculation, it's like, I've never seen this before. And some of the folks have looked at it and like, well, isn't that just obvious? But unless it was published and it became well known, then a lot of times we wouldn't hear about something. All right. So occasionally you come across things, and sometimes it's like, all right, I have no idea. I can't make any sense of this. So you get something like, oh, this is a weird thing. And, I'll take some random screenshot, put this somewhere. You look at it a little bit, you spend a little time, and like, okay, you get certain number of digits accuracy. It's a very interesting thing if it was there. Okay, you explore it. Um, and then you get some things where, like that little box thing, where it's like, all right, it gets all the dang digits, and it leads you to a four-dimensional platonic solid, and you're like, I'm getting the biggest woo-woo vibes right here, so I feel like that makes me not want to even pay attention to it. But then again, I'm like, the crazy thing is, if there actually is something to what that is saying, and these closed forms and the actual corresponding magnitudes have something to do with it, it is very suggestive. Um, I also haven't really talked about it much since then until Nick more recently said, yes, I'm using this four-dimensional platonic solid to model qubits, which happen to be the 600 cell, which is smaller than its dual, the 120 cell, the hyperdodecahedron. And, oh, God, that would be such a crazy thing. But uh, then you'll see things like that. And it's like, when other people are talking about similar things, I feel like more and more folks should know what's kind of going on. Because kind of like I technically Dr. Mike on. He was, oh God, I forget his last name. Uh, he was on with Anastasia and Shiloh on their podcast and everything. He was talking about water because basically he had finished studying and everything, and he was about to go into a lab to do some research for a couple of years, and then the pandemic hit. So basically, he just had 3 years to sit around in like Arkansas, and he's just like, all right, well, let me do some research. Let me research the history of water for the past 60 years. He goes into deep dives. He's learning about all these different aspects. And he keeps on coming across this very interesting thing, apparently, with Young's modulus of water, of how we would typically think, all right, you have a little disturbance. It's going to do its little spin thing. Atoms will bump into each other and it'll transverse through. Water has a habit of flipping literally like a square lattice pattern. It's literally, you can use like Lieb's square ice constant and stuff, and it seems to have remarkable properties with it, where it's like it's flipping around. It's like the communication within the medium of water seems to go faster than we would normally expect it to. Now, and again, there's probably some caveats on there, but it's a very interesting thing that happens. And it seems to have been discovered multiple times by different teams that, as far as he could see, have no contact within each other. They're in slightly different areas. And he's like, well, if all these different groups are running across these same phenomena, maybe I should document. Now he's actually writing stuff up because he's like, well, I spent all this time learning it, so now I actually got to put into words, submit for publication, and everything. I resemble that, and you spend more time on doing all the things, but it's um, pardon. Just the thrill of searching for something. It's so satisfying. It's so satisfying, especially because like you're going down one route and you're like, "Oh, this doesn't work," and every once in a while you find a gem, and you're like, again, could be wrong, could be totally wrong, but let's go through why. Could totally be wrong, but if we happen to use our little number that we have up there, it might be able to tell us something. So let's wrap up with that. Where are we at? All right, so we got our. Let's see if okay. So we've got our crazy number here. Here's our crazy number. 8.3 times 10 to the 61. All right, density. All right. So what happens? Do something. Let's do something weird. Let's take that mass. Let's unlock its energy. Multiply it by c squared because, well, duh, because we can. Okay, what number shall we get? Get a bigger number. 7.488 times 10 to the 78 kilogram. Excuse me, Newton meter. 10 to the 78 joules. All right, ginormous number. All right. Well, what is this? This is energy. All right. Well, let's put it under some pressure, or excuse me, over some pressure. Why? It's we're gonna divide by the Planck pressure. Under pressure. Why am I doing this? Oh, look, we get that same Planck length times 1 meter squared. Okay, well, duh, it's going to be the same thing because it's the C, because you, okay, full disclosure. You take the Planck density, you multiply by c squared, you get the Planck pressure. It's listen. Again, it's a cheap little parlor trick. It's the Planck pressure. Okay, I'm just being straight. We were essentially expressing the same thing, just in slightly different terms. All right. Oh yeah, and this might be why you kind of get the whole 122 orders of magnitude difference, because the actual vacuum energy is about 10 to the minus 10 joules per cubic meter. Whereas if you're going to, I think it's quantum field theory, if you're going to assume Planck energy per Planck volume, yeah, you get a much more ginormous number. Uh, but again, was that what they were actually looking for? Was that just the thing that came out of QFT, quantum field theory? I think that's how we say that. I'm not a professionally trained physicist. I'm just a dude on the internet. But if we go back to here, all right, go back one. Okay, we've got estimated or conjectured mass of universe. 8.3 times 10 to the 61 kilograms. And let's unlock that energy by doing the c squared. Okay, we get 7.488 times 10 to the 78 joules. Massive amount of energy. Okay. Let's divide it. Or excuse me, let's look for another thing. I don't think there's a Planck spring constant, but if we do like mass divided by like time squared, what do we get? We get the spring constant. What are the dimensions of the spring constant? Mass divided by time squared. It's got that -2 in it. The mass divided by time squared is the spring constant. Wait a second. Why does this number look like this number? What's going on here? Why does it take, if we take the estimated mass of universe from our earlier calculation, we multiplied c squared to get the mass energy equivalent of claimed within small u universe. We get 7.4488 times 10 to the 78 kilograms meter squared divided by second squared. But if we take the Planck mass divided by the Planck time squared, we get the Planck spring constant, 7.488. 7.488 times 10 to the 78 times 10 to the 78. That's kilograms over seconds. Need a second. It's kilograms times meter squared over. Oh my God. Is it about to do what I think it's going to do? I don't know. I don't know what do y'all think's going to happen? What was the adjoining factor earlier when we were looking at our conversions? It's like the claimed mass energy of universe within that form divided by the Planck spring constant, and we get 1 square meter. We get 1 meter squared, my friends. WTA. It's about 14 Domino's pizzas in area. Oh, that's kind of like that's about a digit off from Alpha. Um, I just think it's a really cool thing. And basically, what is this? When we take all our different conjectured things there, like this mass and everything, because earlier we done the radius and the length, it was about 100 million times larger. All right, 8 times 10 to the 61 kilograms. All right, so again, 10 to the 8, so about 100 million times larger than the ordinary matter in universe, and there might be reasons for that. I think it's a very neat thing, and at some point, will we be able to test this? That would be really neat. I mean, what the heck? I mean, you can say all these words, but if it doesn't help at all, then well, yeah, what's the point? We're trying to get better. We're trying to level up. I should throw that shirt on at some point. Uh, well, if one could establish a tangent across the distance, one need into do not have enough mental energy to deal with that. Right? No comment. No comment. I'm not. It's well. See, this is the thing, Hex. If you start people, I hear folks say universal consciousness, and then it's like, well, if consciousness is built in, that explains things. And then I have the very weird idea. I'm like, what if universe was alive? If life is built in, doesn't that solve more problems? I'll leave you that on that rampant speculation, folks. Um, Again, we'll keep on pushing on, but for now, take care of yourselves, everyone. It's a crazy one out there. I know there's some really crazy weather. Literally had a reef blow right off the door, go across the car. It's like I was so glad because I was outside and it didn't set off the airbag. So that's probably a little save right there. But other than that, take care of yourselves, everyone, and live long.